All right, in homework 5.8, we are solving differential equations. It's our last unit of the year. So I think we're going to do number 2. Consider the equation dy dx equals 2x over y squared. Draw a slope field for this differential equation, and it wants it at these points. So when you're drawing a slope field, you're just graphing what the actual function is by graphing the slopes of that function. So when x is 0, as long as y is not equal to 0, 0 divided by anything is 0. So we're going to have slopes that are horizontal lines. So I'm going to draw those in. So whatever the function is, the solution will have a horizontal line there, a horizontal tangent line. I'm going to start using when x equals 1, y equals 2, various y's. When x equals 1, whenever y is 0, it's undefined, and dividing by 0 looks like a vertical tangent line. So there are going to be these vertical tangent lines here. When x equals 1 and y equals 1, we get 2 divided by 1, which is 2, and that's steep. So it's kind of a steep line. When x is 1 and y is 2, we get 2. This is at 1, 2. 2 times 1 is 2. 2 squared is 4. So we get 2 over 4, which is 1/2. That's a flattish line. Looks kind of like this. X equals, I think I'll just take, y equals 1 and do various x's. So when x is 1, you get 2 over 1. When x is 2, you get 4 over 1. So that's even steeper. When x is 3, you get 6 over 1. Very steep, but not quite horizontal. When y is 2, we get, I guess I should go do the negatives real quick. So negative 2 divided by 1 is negative 2. 2 times negative 2 is negative 4, divided by 1 is negative 4. So we get these steeper lines like this. When y is 2, we're dividing by 4. So 2 times 2, we get 1. We get 4 divided by 4, which is 1. That's where that line should be. And then we get 6 divided by 4, which is 3/2. So a little bit steeper. On this direction, we get a flat line here because when x is negative 1 and y is 2, we have negative 2/4, which is negative 1/2. This is what a slope of negative 1/2 looks like. Negative 1, and a little bit steeper here. In the negatives, it's exactly the same. So when you graph it, you end up with these slopes that get steeper and steeper the further down and the further, oops, this is wrong. Yikes, sorry, that was bad. The further to the right you go, the steeper they get. The lower down you get, the flatter they get. Okay, so it looks something like this. Sorry, this should be flat, this should be steep. It's the same deal here. So flat, steeper, steeper. So all of these are coming from just plugging in the x and the y and graphing what the slope is. So this graph ends up looking, I don't know, kind of like this, something like this, which is weird. Okay, so let f of, this is the key part of these problems, let y equals f of x be the particular solution to the differential equation with the initial condition f of 0 equals 1. So when x equals 0, y equals 1. That's actually this point right here. So it's going to end up looking, kind of going over and up, over and up. Looks kind of like that, something like that. Write an equation for the line tangent. Oh, this actually isn't the key part. Write an equation for the line tangent to the graph of f at 0, 1 and use it to approximate f of 0.01. So equation of a tangent line is one of our important things. It's y equals m times x minus x1 plus y1. So it's y equals, I'm going to need the m there. So I'm going to use the derivative. So the derivative is at 0, 1, 0 divided by 1 is 0. So f prime of 0, f prime, I guess we should say f prime of x evaluated at 0, 1 equals 0. So it's going to be 0 times x minus 0 plus 1, which is 1. So there's a horizontal tangent line right there. The equation is y equals 1. And the approximation of f of 0.1 is you just plug in 0.1 here. So it's 0 times 0.1 minus 0 plus 1, which is still 1. So we still get y equals 1. All right, find the general solution. This is the important part. finding the general solution for f of x and finding the particular solution. Finding the general solution, we take our differential equation and we separate the variables. We need the dx's multiplying on the right side, so we multiply both sides by dx. We need the y's to be on the side with the dy, so we need to find a way to get the y's over to here, to the left side, so we multiply by y squared. What we end up with is y squared dy equals 2x dx. From there, we just integrate both sides. So we get 1/3 y cubed plus c, although we don't need the plus c, I'll show you why in a second, equals x squared plus c. We only need 1 plus c because we only need 1 plus c because the plus c here could just be subtracted to the other side to make a plus c. So we solve here. To get rid of the 1/3, we multiply by 3. Y cubed equals 3x squared plus, it's again another c, I'm going to call it c2. When we multiply a constant by 3, it's still a constant, it's just a different constant. So y equals the cube root of 3x squared plus c2. This is the general solution. It also wants us to find the particular solution when x is 0 and y is 1. So 1 equals the cube root of 0 plus c2, c2. Cube both sides, 1 equals c2. So the particular solution, we found what c2 equals, is y equals the cube root of 3x squared plus 1. And that's our final answer. All right, I don't think anything particularly crazy or different on the backside. You're just trying to match up the slope fields and solve another differential equation. Again, the slope fields, you just calculate the slope at various points. So for instance, the actual equations here will look like their slopes. So sine of x, when you graph the slopes of sine of x, it will look like sine of x at least one point. So you just look for the one that looks like sine of x. Good luck on the rest of your homework. I hope it goes well for you.